Thank you very much, Rene, for the nice introduction.
Oh, this is very strong.
I'm very grateful for the opportunity to present this work here and to meet with our community again. I appreciate very much this recognition and the chance to talk about the research. Before passing to the talk, I want to mention one of our colleagues who was one of the founding fathers of our community, Peter Kahl, who unfortunately passed away very recently. Peter was a unique figure in our community. He was one of the people who put this community together. He organized meetings and seminars at his Institute of Operations Research at the University of Zurich. He made also a very special contribution to our community by inviting young scientists from Central and East European countries to stay with him at the Institute of Operations Research, be exposed to his projects, have an opportunity to advance their research agenda. One of these young researchers was a young scientist from Poland. It was 32 years ago, who spent there 2 years between 1986 and 1984 and 86. The name of this researcher was Andrzej Ruszczynski. He's your speaker today. And I'm absolutely sure that without this opportunity, I wouldn't be able to advance in this research so far and to be able to give this talk and many others and have these results that Rene mentioned. So Peter will always stay in our memory. I wanted to talk about today about dynamic risk optimization and control. So the most important thing is that how do we evaluate a risk of a random sequence of costs? We have a sequence of costs coming in sometimes 1, 2, up to large T. They are denoted here by Z. These are random costs. And we want to evaluate, we want to calculate a fair value of this cost today. Adjusted fair value of this cost, all these costs today. How much we would be willing to pay today in order not to deal with these costs. The most important observation that we have to make when we deal with such a problem is that this is not a one-time question, because dynamic problems occur when we have to make decisions as time goes on. So we shall have to evaluate these costs also tomorrow and the day after tomorrow and so on. Therefore, dynamic risk measurement is necessarily associated with a system of evaluations. And they are called conditional risk measures. They take as their argument a tail of this sequence, tail starting from a little t and ending with a large T, and return a random evaluation measurable with respect to the sigma algebra at the time when the evaluation is made. This means that at the beginning, when we have to evaluate the entire sequence, maybe sometimes I'll also point here. Stay away from those speakers. Yeah, okay, I turn this way. I just have to stand this way. Okay. So at the very beginning, when we have to evaluate the entire sequence, we shall obtain just a number. How much are we willing to pay today for this random cost? Tomorrow, we shall deal with the subsequence starting from Z2 to the last Z. And of course, the outcome of this evaluation may be different depending on what happened today. And the day after tomorrow, even more of that, okay? So the values of these conditional risk measures are random, but they are less random than the future. They reduce all the future uncertainty to the random variables that are measurable with respect to the corresponding sigma algebra. This is best illustrated on a tree. At the beginning, suppose that we have a stochastic process with 4 stages and with discrete distribution given by this tree. Okay, so at the very beginning, when we want to evaluate the risk of this tree, then of course the one number will be evaluated here. Okay, now at stage 2, we shall evaluate of whatever is to be seen after stage 2. Now, necessarily, we shall get 2 outcomes, okay, depending on what happened in stage 1. That's exactly what I mean by saying that the conditional risk measure has random values, okay? The random values, they are random, but obviously not as random as everything in the future. It reduces the whole uncertainty in the future to something that is measurable with respect to the corresponding sigma algebra, okay? Now, if we have nonlinear risk evaluations, the fundamental thing, the fundamental property is that of time consistency. How do we make sure that our risk evaluations do not contradict each other? Okay? Here is the definition that I find most convenient in this context. We would say that a dynamic risk measure, which is a collection of this nonlinear evaluation, is time consistent if it has the following property. Whenever 2 random sequences are such that they coincide between time tau and time theta minus 1, almost surely, so they coincide almost surely between these 2 times, and at the future time theta, the subsequence z is evaluated as better than w, then today, I mean at time tau, we also have to evaluate z as better. Because if in the meantime they are identical, in the future one looks better, this one that looks better in the future should look better today. Okay? This is very natural, and one would ask the question, why do we really need such an assumption? And indeed, if we deal with just conditional expectations, we wouldn't need it because this would be satisfied automatically. But if we deal with nonlinear evaluations, and here is the whole risk theories about nonlinear evaluations, we really have to make sure that we impose this condition. Otherwise, our results would be not valid. It would make very little sense. Now, it turns out that if this time consistency property is satisfied, then we can dramatically simplify the structure of the risk measures. We define a one-step risk evaluation as the risk of a very special sequence, which has 0 today, something random tomorrow, and zeros to the very end. This is just one-step risk evaluation. And it turns out that the entire dynamic risk measure can be expressed in terms of these one-step risk contributions. If we assume very natural conditions that the risk of 0 is 0, and the current cost, which is known at time t, can be taken out of the risk, a translation property very well known in the static case, then every dynamic risk measure can be represented in terms of a nested composition of these one-step risk evaluations, of these one-step risk measures. These little rows displayed in the red color. So this means that we have here, for time-consistent risk measures, generalization of the well-known Tower property of the conditional expectation. We all know this formula. If every little row is replaced by a conditional expectation with respect to current sigma algebra, then this is a Tower or telescope property, depending in which language you had your class of probability. This is exactly the same property, a generalization of this property to nonlinear evaluations. Expected value is a linear evaluation, risk is a nonlinear evaluation, but this property follows from time consistency.
Andrzej, go on.
Yes? So now, this is also very convenient for us because these one-step risk evaluations are objects with which we feel very comfortable, because the theory of static risk measures is exactly a one-step risk evaluation. So what we need to do is just to take our well-understood static risk measures and plug them in here for these one-step risk evaluations, and then we can obtain a dynamic risk measure of the properties that we postulate, okay? So, for instance, if you use coherent one-step risk measures, we all know the axioms of coherent measures of risk. In the context of these one-step risk evaluations, they don't have real values, but rather they convert something random tomorrow to something less random because it's of today. Okay, so the future sigma algebra at time t plus 1 something measurable to the sigma algebra at time t. And these are the very well-known axioms of convexity, monotonicity, predictable translation. So predictable translation is the same as translation, but just the component Z is measurable with respect to earlier sigma algebra and W with respect to the future sigma algebra. That's why Z can be taken out. And many people worked on these conditional risk measures, and many interesting properties have been developed. Okay? So the example is, for instance, a well-known mean semi-deviation risk measure that we know in static risk evaluation can be written as a conditional mean semi-deviation measure by just replacing every expected value by conditional expectation and the deviation, semi-deviation by conditional semi-deviation. Okay? So this is a purely mechanical operation which allows us to create such conditional, one-step conditional risk measures. So we can use very many of them, conditional value at risk with semi-deviations. We can use entropic risk measures, mix them in any way we would like to do it, okay? Oh, now the other very important property of dynamic risk measures is the so-called local property. Okay, so mathematically, local property can be formulated as follows. If I take a random sequence and multiply it by a characteristic function of a certain event from the current sigma algebra, from sigma algebra at time t, then such a homogeneity property should hold. Then the risk of this sequence should be the same as the risk of the original sequence multiplied by this for this characteristic function. So what does it mean, actually, this local property? Okay? It means the following thing. Okay, let me go here. If I have a certain random, this is the same example as I had before. If I have a certain random sequence, Z, and evaluate the risk of this sequence at time 2. So I know that I obtain two different numbers depending which side of the tree the sequence ended, okay? And then if I replace the blue Z's by zeros, then the evaluation of these zeros will be 0, but this number will not change. This number will not change, okay? This means the evaluation of risk here does not depend on the outcomes that are impossible, that cannot happen once we are there, okay? This actually does not follow from any of the statements that I did before, except for coherent case. This is automatic for coherent conditional risk measures. However, if you would want to work with non-coherent risk measures, then you have to specially assume this condition. And this condition is of profound importance, of course, for applications. You wouldn't want to have your risk evaluation here depending on what can happen here, which actually it cannot happen. Okay? Now, the other fundamental property in risk evaluation is low invariance. Low invariance is extremely relevant because in applications, we deal with data. So we necessarily get information only about the distribution of random outcomes rather than about some abstract space, omega, with sigma algebras and little element. These are mathematical constructs that allow us to develop the theory. So in the static case, a risk measure is low invariant if such an implication holds. Whenever two random variables have the same distribution, we evaluate their risk as the same. Okay? This doesn't follow from the earlier assumptions. It has to be assumed additionally. Okay? So this low invariance is a very well understood property, which has very many implications in the theory of risk measures that I have no time to visit to develop here. Okay? Now, in the dynamic case, if you wanted to talk about low invariance, that we have to go back to the first transparency and remember that our intention is to make decisions as we go on. So we are interested actually not only in the distribution of a random variable, but actually in all conditional distributions. So, for instance, we can define, and I propose to think about low invariance in dynamic case, about low invariance with respect to conditional distributions. So if we have two random outcomes at the very final state, whose conditional distributions under all conditions from time 1 to t minus 1 are the same, then we would claim that all conditional risk measures should be the same. So equal conditional distributions, equal values of conditional risk measures. This would be an extension of law invariance to the dynamic case. Now, it is tempting to think of a law invariance in the dynamic case from the static perspective. But if we defined a law invariance in a static way, this means if only the final cost is the same as identical distribution, Z has the same distribution as W, then the risk measure looked at from the initial state is the same. Then if we had law invariance in this static form and time consistency, then we would restrict the class of all risk measures to very trivial examples, only expected value or the worst case. And in continuous time, you would have the entropic risk measure, okay? So this is due to the fact that, there are very many random variables that have the same distribution. However, if looked conditionally from the intermediate stage, they look completely different. And therefore, assuming that the risk measure is the same is too much. Now, how can we use these dynamic risk measures in multi-stage optimization problems? Okay? So suppose now that we have a probability space with this filtration from F1 to Ft. These are sigma fields here. And we have now decision variables x at each state, x with index by time. Okay? Now, we all know that the fundamental requirement in stochastic optimization is that of non-anticipativity. Our decisions, viewed as random variables, should be measurable with respect to the sigma algebras at the current state. So they should not see the events that are not distinguishable at this time. Okay? So they only depend on the past. Okay? And if we have a cost z at each stage, okay, then we may try to optimize the sequence of such costs by using a time-consistent dynamic risk measure. Okay, so we use a time-consistent dynamic risk measure to optimize the sequence of these costs. Now, as we remember, time-consistent dynamic risk measures under these simple assumptions that I presented earlier, they have a very special structure. They have a structure of such a composition, nested structure of this one-step conditional risk measures, one-step risk contributions. And they are monotonic and satisfy these conditions that I mentioned before. Okay? Now, by using the fact that that we have such a nested structure, we can derive, of course, under some technical requirements, which I'm not going to present here, a very important interchangeability property. So we can look at the dynamic optimization problem in two different ways, both extremely important. One is optimization with respect to functions at the very beginning, each of them measurable with respect to the corresponding sigma algebra, or we can look at this in a nested form in which optimization with respect to every decision is pushed down to the stage at which it actually is used. Okay? This can be done because rho 1 is monotonic, so x2 can be pushed under rho 1, and rho 1 and rho 2 are monotonic, so x3 can be pushed under rho 2, and so forth. Okay? So we have this nested structure that is of a dynamic programming character. Okay? So on this scenario tree that I had before, okay, we can look at our problem either from the very beginning as a problem in functional spaces with the optimization in functional spaces, or we can look at this problem the other way. We can look at the bottom and optimize with respect to the decisions that I made at the very last stage. Of course, this optimization depends on whatever happened in the past, and then go backwards and fold these functions up up to the first stage, okay? So this is due to the property of time consistency. We wouldn't be able to do this if we didn't have time consistency, and if we didn't have local property here, because obviously this local property is fundamental, that these functions that are optimized here actually depend on these guys that are linked by this stage. Okay? Now, I want to pass to the main the main topic of this talk is the use of risk measures in control problems. So, in control problems, we have two types of variables. These are the variables that we choose to act on the system, and there are internal system variables that depend on our actions and also depend on some random exogenous influences, okay? And of course, there are very many control systems. The most important from the point of view of applications are Markov control models. So in the Markov control models, the system variables are state variables. And the state variables have this feature that if we know the value of the state variable, and we know what controls are we going to apply after this time, then we can statistically describe the evolution of the state in the future. Okay? We don't need to know how did the system come to this state. We only need to know the value of the state, and we need to know the statistical properties of the control after this time. Okay? So this is a very important property of Markov systems, and that's why they are very successful in applications, and most of applications of control problems are of Markov systems. And the main objective is to find the control policy. How do we choose the actions to influence the state in order to obtain good statistical properties of the trajectories that the state can go through, okay? For this expected value of some costs, okay? Now, we want to use risk measures for this kind of problems. And before I start with some formulas, I want to make three very simple observations, but I'm absolutely convinced that if you just take out of this talk these three observations, that I'll be already successful, okay? The first thing is such, that the cost process depends on the random trajectory of the system. This is a trivial thing, okay? System evolves in the random, and some costs are calculated. The second observation is more important. We don't need to have a theory for measuring arbitrary sequences of random variables, arbitrary stochastic processes. We only need to measure the risk of this class of processes that can actually occur in the system. So our arguments of the risk measure are very much narrowed, okay? And this can be used to big advantage, actually, okay? And the last observation, which is objective of research, is that we need to have risk measurements should be a function of the current state, because we want to obtain also policies that depend on the state. We don't want to keep in memory how did the system get to the current state in order to develop our actions, okay? So the first is obvious. The second one is just an observation, how we can simplify the research. And the third one, what we have to keep in mind for our research to bring us some results that are of some use, okay? Okay, so let's start from the very simple application, but already, I believe, interesting, with controlled Markov chains. So we have a controlled Markov chain with the state space X, control space U, and a control transition kernel, which is a mapping from the states and controls into the set of probability measures on the state space, okay? So we have if I have a state and control, then we shall get a probability of the next state. And there is a certain cost depending on state and control. We shall use H as a history of the state. And the policy can, in general, be history dependent and takes the history and gives us a certain action. And if a Markov policy would be a policy that takes just the last state and calculates the action. Okay, so the system works as displayed on these green lines. Once we have a state, a Markov policy, if we use a Markov policy, would calculate a control U as a function of the state. And then the state and control pair will give us a distribution of the next state. Okay, this is the system. Okay, and then let's use a risk measure to optimize this system. Okay, so we have this controlled Markov chain. Pi is the policy. We have a cost sequence Z. The cost sequence Z depends on the state and control at each time. And we use a time-consistent risk measure, here, the time-consistent risk measure, to evaluate the risk of this cost sequence that is generated by the policy. So this time-consistent risk measure is obtained by composition of different one-step risk evaluations. And our cost problem, this is a finite horizon cost problem, would be to minimize this risk measure with respect to all policies. Okay? And then, of course, what are the difficulties here in this case, which are common for all problems of this type? The probability measure on the space of trajectories is a function of the policy. Therefore, all the spaces are indexed by this policy. The processes are indexed. The state, obviously, process depends on the policy. The cost process depends on the policy, obviously. Okay? So then the risk measures also are depending on the policy. They don't only evaluate the cost that depends on the policy, but because they act between different spaces, that the spaces depend on the policy, everything is indexed by the policy. So we have to somehow get a risk theory that encompasses all these probabilistic models for all possible policies. One policy, one probabilistic model. Another policy, another probabilistic model. We have to have all probabilistic models under one umbrella to be able to compare different policies. Okay? And now, obviously a very important feature of this problem that I put it in red, that we really need to measure risk of these random sequences that may actually occur. So actually, this is absolutely clear that if we define as the fundamental, the space large omega, the space of all state trajectories, it will be sufficient. If you know state trajectory, we know, and we have a policy, we can evaluate the risk. That's what we said, we have this, okay? Okay, so then we can, for this kind of problems, we can refine the concept of time consistency and integrate it with the local property and actually conditional law invariance, okay, in one shot, okay? So let's say we have a history of the state, we have a process of costs depending on the policy, and of course, if we know the history, we know the value of Z, okay? And we say that these risk measures are stochastically, conditionally time consistent if they have the following property. Whenever two policies, pi and pi prime, give me the equal cost at the current time, given current history H, and the risk counted from the next stage of the first sequence under the first policy, pi, is stochastically smaller than the risk of the second policy, pi prime, then we have to look at the risk of the first policy at time t as smaller than the risk of the policy pi prime at time t. Okay? So this is very similar to the concept of stochastic, of time consistency that I presented before, except for two changes. First, the conditions here are conditioned on the history. So instead of looking at this as random variables, these are now numbers. Because it's conditional, they are both known. And the second thing, these random variables in the future are compared in terms of first-order stochastic dominance rather than a plain inequality. I could have written here plain inequality, but for Markov models where only distribution matters, dominance is a more natural comparison than the plain inequality, okay? Because the only distribution is described, okay? So now the second step is, as I said, we would like to have the risk evaluation dependent on the state. We have to postulate that. This doesn't follow from anything. So we shall just assume that if we were to use a Markov policy, which means a policy that depends only on the current state, then the risk evaluation would depend only on the current state, okay? So formally, this is the following. Whenever I have two histories, H and H prime, that happen to have the same current state xt, and I use a Markov policy, then the risk evaluation of the future should be the same. Risk evaluation should not depend on how I got to this state, but rather where I am currently now, okay? So then I can write the whole thing as a function of the state, okay? And then, this is a busy transparency, but I want to summarize what it is about here, okay? I use the symbol V for the value of the policy. So currently, since we allow policies that are history dependent, okay, the value of the policy would be history dependent. Okay, and this is the risk of all the future costs that this policy will generate. Okay, now it turns out that if I postulate this time consistency and a Markovian property of the risk measure, then the values of the policy are related by this last line of this transparency. Unfortunately, this is at the very bottom. And I want to explain this line because then other things will also be related to this. So the risk at time t can be expressed as the cost at time t and a certain mapping that takes three arguments. The first argument is the current state. The second argument is the distribution of the next state. This distribution of the next state, obviously, is a function of control. And the third argument is the risk of the next history. Is the risk of the next history. Now, if a current history is known, then the next history will be the current history and the next state. So this means that the three arguments of this operator sigma are current state, distribution of the next state, and the value function at the next state, okay? For Markovian, it's explicitly written, because then I have the value of the next state, cost, and this mapping sigma. So this statement says, if I have dynamic risk measure that satisfies this time consistency and Markov properties, then such mapping sigma exists. And the other way, if I take such mapping sigma that are low invariant risk measures with respect to the last argument, when the second argument is the probability distribution, then by using them here, I obtain a time-consistent Markovian risk measure. So this is if and only if. Therefore, in Markov models, instead of dealing with this complicated conditional risk measures that take the whole tail of the sequence and map it back to the current space, it is sufficient to specify these transition risk mappings. These are static risk measures on the space of function of the state. So they don't completely depend on time. Okay? At any time, we have the same space, the space of functions of the state. And we can derive this transition risk mappings from classical coherent or non-coherent, generally one-step risk measures. We can derive them in such a way that we take a risk measure, for instance, a mean semi-deviation or average value at risk and so on, and we look explicitly how does the probability distribution affect the value of this risk. because the probability distribution has to be made an argument of this sigma. And this is the only difference from the risk measures that we know, okay? Because it's controlled, so it has to feature as an argument of this, okay? And then if we use this type of risk measures in the dynamic problem, then we can pass to risk-averse control problem, and we obtain the dynamic programming equations. At the last stage, we optimize the cost, and then going backwards, we optimize. We have a dynamic programming equation in which we minimize the sum of the current cost and the risk of the next value function. In case of coherent risk measures, we have the maximum of expected values with respect to some set of probability measures. This connects to the expected value case, in which case we would have just this mu specified as Q, because the probability distribution of the next state. Okay? So this can be developed further. Once we have these dynamic programming equations, we can have infinite horizon, we can have solution methods. I have no time to talk about this. Maybe I quickly mention about two extensions to continuous time, because it turns out that we can also use similar ideas for continuous time models. So if we consider, for instance, continuous time Markov chain, in which we have a transition function, which is nothing else but the transition probability in the small time interval, okay? And the transition probability in small time interval is proportional to this time interval multiplied by something that is called the generator of the process. These are transition rates. So in the continuous time, instead of transition probabilities, we have to talk about transition rates, okay? And the cost of the system, instead of the sum, we have an integral of the cost of the state and the sum cost of the final state. Okay? Now, we can have a concept of time consistency for this particular continuous time model as well, okay? And we say, if we have stochastic dominance between risk evaluations in the future, then we have to have inequality between risk evaluations today. Okay, this is the idea that we talk about. So the risk is basically consistent with stochastic dominance, okay? And we can also define Markovian measures by these, that risk of the future cost depends on the current state, not the whole history of the state. Okay? And now it turns out that in this case, we can develop a similar structure. We can say that the risk of the current state is cost accumulated in a very short interval plus a certain nonlinear mapping of the risk at the next state after this short interval of time. And this mapping is very similar to what we have seen before. It takes the current state, the distribution of the next state, which we know this is a transition function, and the value function at the next state. Now, here comes Darinka will tell you much more on Thursday about this, because I'm very short in time here. But we can use a dual representation. If we assume coherence of this transition risk mapping, we can use dual representation. We can use multi-valued calculus. So we can do the differentiation of multi-functions, okay? And we can represent this sigma very closely for small epsilon as the value at the future state and a certain support function of a certain set. Now it turns out that this set is associated with the generator of the system. It's something larger than the generator of the system. We call it a multi-generator, okay? And if we do this, then we can develop a backward Kolmogorov equation to calculate the value of the risk. This is ordinary differential equations in which the multi-generator, the support function of the multi-generator features. Here is this support function. And in the expected value case, this would be just a generator multiplied by the value function. In this case, it is slightly more complicated. But Darinka will talk about this on Thursday, so I'm not going to steal the show from her, but this, again, this type of structures can be derived, okay? And the last applications, the last class of problems I wanted to mention is the control of diffusion processes. So these are continuous time models in which the state is also continuous. And here, let's look at this. This is the state dynamics. It's developed by a stochastic differential equation. In this stochastic differential equation, X is the state. It's a vector state, multidimensional, okay? B is some drift function, okay? S is time here. And sigma is a matrix. W is a vector Brownian motion. And sigma is a matrix of volatilities, okay? And they all, both the drift function and the matrix of volatilities, depend both on the state and on our control U. So this stochastic differential equation describes a certain stochastic process, a diffusion process, controlled diffusion process. If I put a different control function, I obtain, of course, different distributions of X. It is a well-known, well-investigated structure in stochastic control theory. Now, stochastic control theory is mainly busy with optimizing expected value of such a function of the trajectory. This is an integral of the running cost. This is C is a cost rate, which depends on the state and action. And psi is the cost of the final state at which the process will end. Okay? So we want to put here a risk measure. We want, instead of expected value, we want to put here a risk measure. If we put here an expected value, there are very many books that investigate this problem. It's a very difficult problem, a very large theory, and very interesting and deep. So we want to use a dynamic risk measure, which is, instead of expected value, this rho 0t. And we assume that it is time consistent. For the continuous time is convenient to write time consistency in such a way that it is a composition. The risk from time t to time r of something random at time r can be calculated in two stages. First from S to R, and then on top of it from T to S. Okay? And it has a local property. Local property, which I mentioned before, very important. The risk value depends only on the events that can actually happen. Okay? Now, it turns out that under very minor technical conditions, if the filtration is given by the Brownian motion, as we have it in this case, then risk measures that have this property can be described by a very specific mathematical structure. And this is called a backward stochastic differential equation. Okay? This backward stochastic differential equation has this is written here, has the final value given. This is the YR, is the random variable whose risk we want to evaluate. And it has two variables, Y and Z. And we have to find progressively measurable processes Y and Z that satisfy this differential equation such that the final value, we hit the proper random variable. Okay? And in this stochastic differential equation, the only object that is of interest is G, which is called the driver of this equation. Now, if we assume that the driver is convex and positively homogeneous, does it depend on Y, that this risk measure will additionally be coherent. So all risk measures are, that satisfy these conditions and little technicalities are given by backward equations. And if we put the driver convex, positively homogeneous, independent of Y, then we obtain coherent risk measures. Okay? And then we can define a value function in this process, in this problem. It's a value function is the cost of running the process from given state at a given time to the very end, the optimal cost. This is the running cost, final cost, but running cost just from time t and the risk from time t. And we can write the dynamic programming equation for this process. Okay? It looks very much the same as the dynamic programming equation for expected value, except for the conditional risk measures are put here. Now, if we put explicitly what it means here, that actually we have a system of stochastic differential equations. One is the forward system that describes the evolution of the process, and then coupled with this, actually it's decoupled because it's coupled only by the final value. It's a backward system that goes backward in time and evaluates the risk. Forward system sees what the random state will occur, and the backward system will calculate how it is worth. Okay? And in the backward system, we see that in the backward system, the running cost and the generator appear together. So we can interpret the generator of the driver of the backward stochastic differential equation, we can interpret as the risk rate in this problem. It says the same function as the cost rate here in this system. Okay? If this was 0, this would be a system associated with the expected value model. If G is non-zero, this is a system associated with the risk-averse model. Okay? So this is the only difference, this blue thing. Okay? And then we know that the expected value model has optimality conditions in form of a certain partial differential equation, nonlinear partial differential equation. And in the risk-averse case, we can do the same. So it's a lot of technicalities, of course, involved in this. But we can derive a risk-averse Hamilton-Jacobi-Bellman equation in which the black part is the same as the expected value part. And the only new thing, so a little thing, but a lot of work to get it, okay, is this part corresponding to risk. If this was 0, we would have an expected value model. But this is G, this is the driver of this backward equation. Okay? And many things can be done about this. Janik talked about this yesterday, so I really don't want to mention, but we can move further with this model and develop discrete time approximations and connect to the Markov chains before. This is a work in progress here. Okay? So the conclusions that I wanted to end up with are the following. The dynamic risk measures for Markov processes have very special structures. And they are defined by simpler objects that are easier to manipulate and work with. In discrete time Markov chains, these are these transition risk mappings and associated multi-kernels. In continuous time Markov chains, these are these risk multi-generators that Darinka will define you in detail on Thursday. Okay? And for diffusion processes, these are the drivers of backward stochastic differential equations to calculate risk, so-called, let's call them risk rates. Okay? To specify a risk model means to specify these objects. If we know how to specify these objects, we can obtain a risk-averse model, risk-averse counterpart of an expected value model. Okay? And the optimality conditions and also numerical methods for these risk-averse models are still tractable, although highly non-trivial, of course, extensions of their risk-neutral counterparts. So the theory can be advanced with effort, but still with the hope to achieve some results of meaning. Okay? Other topics that are associated with this line of research, okay, and some of them are discussed here at the conference, are partially observable Markov processes. Very interesting application to clinical trials where risk aversion appears to beat the expected value model in expectation, which is something that you probably think is something wrong, but indeed it happens if you use approximations of both models. Continuous time Markov chains on both on Thursday, okay, and diffusion processes. This was already yesterday, and I tried to allude to this today. And I have some references here, but I have no time to talk about this, so that's what I wanted to finish with. Thank you very much for the attention.